So this is the typical furnace and LPCVD equipment you can find from any clean room area. We're gonna have a tour next week in the clean room, and then I'll show you, what kind of furnaces are there. Actually, these are all similar to each other. This furnace, we say that there are 4 banks. Bank number 1, 2, 3, and 4. And the highest temperature is at the highest level bank. Usually they use this top bank for oxidation furnace. And then the other banks, actually the temperature is like, so here the top bank temperature is 1000 to 1200 degrees Celsius. This bank could be 600 degrees Celsius, maybe 600, and then 400. So all these 3 banks actually are used for low pressure chemical vapor deposition, not the oxidation. Okay, so this is the cross-section view of typical furnace. There are 3 zone heaters and pressure equipments, So if you wanna have a deposition rather than oxidation, you can think about the use of LPCVD. All right. So in case of the LPCVD, you need to think about some characteristics. So low pressure chemical vapor deposition, LPCVD. The general characteristics of the LPCVD is basically the deposition of thin films. So thin films are deposited by chemical reaction at an elevated temperature. Temperature is a very important element to promote the chemical reaction. Okay? So usually this chemical reaction is triggered by the temperature or the heat. Okay? In that case, we call this low pressure chemical vapor deposition, because we lower the pressure to make the molecular mean free path as long as possible to drive the whole process into the process governed by reaction limited process rather than diffusion limited process. So temperature used here is in the range somewhere from 400 degrees Celsius to 700 degrees Celsius. It's a little lower than the oxidation temperature, which is above 900 degrees Celsius up to 1200 degrees Celsius. And some cases, you don't want to elevate the temperature too much because of the reasons that we'll think about from now on. In that case, instead of heat, you can use the plasma to cause this chemical reaction to occur. In this case, we say we use plasma enhanced chemical vapor deposition. Okay, so I'm gonna quickly cover PECVD later. In this case, the temperature range is much lower than the LPCVD temperature, 200 degrees Celsius to 350 degrees Celsius. Instead, you have to compromise the film quality. Okay, so the film quality will be pretty low in this case. Low quality film. Okay. Well, why this gap is important between 350 to somewhere around 607 degrees Celsius? Well, in many cases, people use metal, especially the metal, something like aluminum, okay? And you don't want to melt the aluminum which already exists on the wafer by putting your wafer into high temperature furnace or high temperature equipment. Aluminum, the melting temperature is 660 degrees Celsius. That's very important, right? And even though aluminum doesn't melt at, for example, 400 degrees Celsius, maybe 500 degrees Celsius, its characteristic start changing from 300 degrees Celsius already. So you don't want to put your wafer into, for example, wafer with aluminum pre-deposited on it into the furnace where the temperature is 450 degrees Celsius. Okay, that's where this PCVD actually functions, because you can lower the temperature as low as 200 degrees Celsius and then deposit some kind of thin film on top of aluminum, for example, silicon nitride or PCVD oxide, even though their quality is lower than either the furnace or LPCVD. Well, also, you guys saw last time that we can spin coat the photoresist, right? And then do the hard baking on top of the hot plate, right? In that case, hard baking temperature of photoresist is around 100 degree to 130 to 140 degrees Celsius. So what will happen if you put your wafer with photoresist coated on it into the furnace? Well, photoresist is the polymer. Obviously, this polymer will just burn, and it will screw up everything actually, because it burns, it produces fume, and it contaminates, all the interior of your furnace and LPCVD. Your clean room needs to be shut down sometimes, so you need to be very careful. So photoresist coated wafer cannot even put into PCVD furnace. Look, the temperature is 200 degrees Celsius, substantially higher than hard baking temperature of photoresist. Hard baking temperature of photoresist. And one of the important characteristics of this LPCVD is obviously low pressure, right? How low is the low pressure? Not super low, but still very low. In terms of torr, it will be somewhere between 0.3 to 1 torr. Remember, atmospheric pressure is 760 torr. Okay, that means 760 millimeters of height of the mercury column, right? And experiment was done by Torricelli, so we named after him torr. Okay. So 1 torr is just a little fraction of the atmospheric pressure. It's 1 out of 760. So it will be very low pressure indeed. but it's not super low. You guys will see that sometimes we have to maintain the vacuum level at a very, very low range for specific deposition, which I'm going to cover later on. Okay, but in this particular case, we can just go down to below 1 torr, which is not very difficult. We can achieve such kind of vacuum by just mechanical vacuum pump. Otherwise, we need to use very special vacuum equipment. Okay, so at this low pressure, what's good? We can maintain very long mean free path of the molecule. What is mean free path? Well, I'm going to explain later on when I explain high vacuum. Okay, high vacuum. But at this long mean free path, basically diffusivity will be promoted. Okay. So what that really means is that gas molecules can diffuse very well, not limited. So it's not diffusion limited anymore. Your process will be reaction limited, only limited by, mostly by the temperature. Okay, so what is good about the reaction limited process? Well, because the molecules that are supposed to react can diffuse very well into any kind of gap. Your deposition will be more uniform. So you can maintain a better uniformity. And at the same time, the whole process is not very sensitive to the supply of the chemicals, right? So less sensitive to gas flow dynamics. Okay, and as a result, we can maintain very good step coverage indeed. Excellent step coverage. This is very important for our multi-scale process later on. Okay, in the multi-scale process, you will have some kind of structures, some kind of maybe roughness, some kind of mechanical structure as well. And in many cases, you'd like to deposit the chemicals around such kind of structures for specific goals. So you see that we can do a very interesting job with such kind of a combination of processes. To be able to do that, you need to have a very good step coverage. For instance, if you have a silicon etched structure, let's say you have a silicon wafer and you etch down into the silicon wafer with something kind of channel, for example, here. And you'd like to cover the whole area, but step coverage is not good. If something is deposited from the top, not diffused very well into this little gap, what's happening will be your coverage will look something like this. Okay? So this deposition is much more like snow, on top of, the roof. So the side wall, there will be no snow. Okay? In this case, we say that this process is diffusion limited. Okay? However, if your process is reaction limited, diffusion occurs so well such that the deposition is uniform or conformal over the whole surface. So we say that this deposition is conformal. conformer. You can even create nanostructures with this kind of approach without nanoscale patterning. Do you need the, for example, nanochannel? Maybe very sharp nanochannel with very sharp corners, because it's pretty well known that the liquid will flow very rapidly around these sharp corners. Here's a way, here's an idea that you can use. For instance, you can have a deep hole like this etched into the silicon. And this deep hole doesn't have to be nanoscale, which is very hard to fabricate. You saw how hard it is, because the patterning is actually limited by light spectrum wave. And if you put a lot of body there, of course, like big companies, you can achieve nanometer scale patterning, but normally, you cannot afford it, right? So in that case, well, for example, here we have maybe micro scale patterns, with our research contact aligner, which can produce, for instance, micron gap. So let's say this gap size is microns. But if you deposit something here, well, the whole process not exactly completely reaction limited, right? More or less reaction limited. So it goes like this, but there might be some different thickness of deposited material, whatever it is, the material we're gonna study from now on, whatever it is, okay? And if you deposit more, it will go like this. Look, now suddenly you can create very little cavity inside, and the size of this cavity is limited by how you deposit the material, limited by the combination of deposition process. And then you can even come up with this channel with very sharp corners here. Is there anybody who wants to try reproducible nanochannel through which you want to flow biological fluid, and see what happens inside? What kind of reaction occurs inside this little cavity? Okay, different from a big volume. You just maintain very small volume, like the small cell, like the small nucleus inside the cell, and see what happens with these molecules. Where these molecules are well crowded. Okay, then there might be totally different physics that comes into the picture. You want to run such kind of experiment reproducibly, this is the way probably to go. Okay, so I just gave you one of a simple ideas to make a nanoscale structures out of microscale patterns. So this is indeed really multi-scale integration by using some special characteristic of this deposition process. Wouldn't that be nice, right? That would be nice. Well, so what kind of material are we going to deposit? For instance, we'd like to deposit here silicon nitride. Okay, and what are the uses of the silicon nitride? Well, there are a number of good uses. Well, first of all, silicon nitride is a very tough material, so you can use silicon nitride as the etching mask. Tough against chemicals. So for instance, you're gonna learn crystal etching with hydrogen peroxide. Sorry, not hydrogen peroxide. What is it? KOH. Okay, KOH. That actually creates the faceted, diamond-like structure etching. But in this case, you need to protect other areas from the etching process. How can you do that? So you want to create the selective etching area. How can you do that? You can use silicon nitride as an etching mask, because silicon nitride is resistant against this chemical, potassium hydroxide. Sorry, potassium hydroxide, KOH. Well, sometimes you can use the silicon nitride as a structural material. It's a very good structural material compared with the silicon oxide, which is normally in huge stress, especially compressive stress. Silicon nitride, you can actually fabricate almost stress-free film, structural material, because it is stress-free. You can make a very flat material because of low stress. Okay. But you can also use this silicon nitride as the mask for oxidation, which really means that you can block certain area from oxidation to occur, so that you can selectively oxidize certain window of the area. Again, silicon nitride is resistant against reaction or the passage of the molecules. You can block such kind of passage of the molecules. Okay. Also, it's a very good passivation layer. For electrical as well as mechanical passivation. Electrical passivation, you can use silicon nitride as the dielectric material, or the material that blocks the passage of the current, or you can use silicon nitride as the mechanical passivation layer with very low friction indeed. So the first micromotor that has been invented at the Berkeley in the early 80s, they use actually silicon nitride as the sort of lubricating layer. It's a very low friction. That's really nice. Okay. Well, why can we use silicon nitride as electrical passivation layer? Because of low resistivity. Resistivity of the silicon nitride is around 10 to the 16 ohm centimeter, which is very low, super low. And also dielectric strength. The strength of electric field, that makes the film breaks down. That makes the film break down. Okay, that makes the film, be penetrated by this passage of the current. That's the strength, dielectric strength. It's very low, very high. Goes up to 10 megavolt per centimeter. This is really huge number. You'll find out later on. Okay. Well, what is the chemistry for obtaining this silicon nitride? That is LPCVD again. Low pressure chemical vapor deposition. Okay. And what's happening here is 3 silicon SiH4. We call this silane gas. 4 hydrogen atoms are reacted with the one single silicon atom. Silane gas. That is a gas actually. Plus ammonia. You know how it smells. You know it smells very strong. Ammonia at high temperature will create stoichiometric silicon nitride, Si3N4, stoichiometric, and leaves a lot of hydrogen gas. So we need to burn this out, you know, to eliminate. Okay. And the temperature will be at somewhere between 700 to 900 degrees Celsius. Pretty high, but not as high as the oxidation temperature. Okay. Look, there's no oxide, there's no oxidation involved in this whole process, so there's no reason why oxidation will occur, you know, on the wafer surface. And you will obtain stoichiometric Si3N4, okay? Well-balanced silicon nitride. However, the result is you cannot really avoid the stress, but this time instead of compressive, you will obtain tensile stress. Sometimes tensile stress is good because if you want to create, for example, thin membrane, you know, membrane in a tensile stress will become super flat compared with oxide membrane in compressed stress. In that case, compressive stress makes the compressive stress will make the whole area wrinkled. You know, I explained last time, right? I've already explained last time. And you can also use PCVD to obtain the silicon nitride. In this case, the chemistry is slightly different. You're gonna be ended up with non-stoichiometric silicon nitride, something like NH. So it's not really pure silicon nitride. It's silicon nitride is something else. It's non-stoichiometric. Instead, the temperature is lower, so that you can actually prepare, you know, for example, metal underneath, okay, and then just run this PCVD to obtain silicon nitride, non-stoichiometric silicon nitride coating on top of this metal. Okay, sometimes you need such kind of combination. And this is less tensile. And sometimes you can come up with the low stress version, low stress version of this silicon nitride, and we call that low stress silicon nitride, which is more expensive and more difficult to run, but obviously you can obtain it, you know. Well, I'll talk about it later. And PCVD is normally less tensile, even though, you know, normally it's less tensile. But the problem is pinholes. Of course, as I explained, you know, normally you will obtain low quality films at low temperature, for example, PCVD. So there are deals, you know, there are compromising strategies that you need to use, right? Instead of this, instead of that, it's like an engineering process. Instead of film quality, you need to use high temperature. Instead of low temperature, you need to compromise the film quality, you know. So it's really engineering, design, and the planning that you need to go through to integrate the whole process. So because of pinholes and low quality, you cannot use this silicon nitride as the etching mask. No etching mask. Okay. So let me show you how you can create certain window area for to obtain the oxide in the specific area. Well, you will have a wafer in the first place, okay? Wafer in the first place. All right? And then you will either grow, maybe grow the first silicon dioxide out of it. How we can grow? Well, we can use, you know, oxidation process. We've already seen how such process can be carried out and how you can understand the physics of this oxidation. You know, at the fast time scale, early time scale, the growth will be linear, and at a longer time scale, the growth will be parabolic, gets slower and slower. You know, we've already seen all kind of mathematical models and physical models of it. And you can deposit and pattern silicon nitride by using PECVD furnace. Is this process comparable? Which means that can we actually mix this process? Are they comparable to each other? Well, look, silicon dioxide, this process occurs at 1000 degrees Celsius, for example. And on top of that, you can deposit silicon nitride at low temperature, which doesn't hurt, you know, the whole process, right? Okay, so you know, this process is really, these processes are really comparable to each other. And then just by using lithography process, you can pattern photoresist on top of it, open the window, and then use some specific chemicals that I'm going to go through later on to etch such kind of window away. This could be chemical, this could be plasma, this could be gases, you know, many different kind of etchant can be used to define or open up such kind of window. Okay, that's what we did. So the whole process is comparable. You can align the whole process. And after this, you can actually go through the oxidation and look. When oxygen is trying to pass through this silicon nitride film, as I said, silicon nitride is resistant to the passage of the molecules. So oxygen has really hard time passing through this thin layer, you know. Instead, the oxygen will react with this open surface of silicon to create the oxidized area. Okay, that's how we can create, you know, a window of oxide. So here you will have the wafer initial oxide, which will grow. Remember, it will grow, and then the volume expansion will occur, you know. That's what I have explained, right? And silicon nitride film will be lifted up like this. Okay, so let me emphasize the silicon nitride film. You know what I'm saying, right? So this specific area will grow by the oxidation. So this process is oxidation. Look, we used the silicon nitride as the oxidation mask. Okay? All right. Alright, finally, another important material that we want to deposit is actually polysilicon. Okay, but to explain, further about the doping physics, I think I'll just skip that part and then cover the polysilicon deposition a little later. Okay, little later when we need to use it for specific goals. Okay, so I'll do that later. Okay, the deposition characteristics, the step coverage, and the stress field in the thin film of polysilicon. Okay, I'm going to explain later on. All right, so let me skip it, and instead, let me directly go over to the doping of the impurities. So how does the doping occur? Doping occurs by diffusion. So you have a crystal of silicon, and on top of the silicon, you would like to deposit some impurities by certain means, which I'm going to explain. It could be ion implantation, it could be furnace deposition, it could be something else, spin coating maybe. Spin coating is also possible. And then you would like to elevate the temperature so that at high temperature, diffusion is promoted. Diffusion of these impurities into the lattice of this silicon crystal will be promoted, and they will actually migrate. This dopant will migrate and then diffused into the silicon crystal. So it is crucial to understand the whole process as this diffusion process. Okay, and because of that, actually, we need to model the whole process and understand the whole process in terms of a physical model and the formula that can be used to explain this doping in time scale and in the coordinate system. All right. So, well, the diffusion process. So let me add up one more slide. What happened to my slide, by the way? Why doesn't matter? Anyways, one more slide. Okay. And come up with the model for this diffusion process. Well, diffusion doping. So it's a process by which the impurities such as P or N particles, such as, well, P is like a boron, N is like a phosphorus. Impurities will thermally, driven by temperature, again, at high temperature, diffused. Okay, so in this whole diffusion process, you need to understand how this diffusion really occur. I didn't cover how this diffusion occur in the oxidation process, because in the oxidation process, the whole process was actually a steady state, and the profile was just linear. However, in this doping process, such steady state never exists. Okay, so you need to model this whole process. So let's take, for example, one-dimensional model like this. Just take a piece of silicon solid, for instance, Well, we can think about generalized three-dimensional analysis, but for more concrete physical understanding, let's just think about one-dimensional doping, okay? And you'll find out that you're going to be ended up with partial differential equation, because it's not only space variable, which is one-dimensional, which is x only, but also time variable as well. So it's a function of two variables, x and t. Let's say in this little piece of material, this material will have a certain area, A, and space coordinate x is like this, all right? And there will be flux. Well, let's say the flux can be represented by maybe Q. Okay, normally people use Q, right? Into this little element, little piece of element, you know. What happens to the other side? Well, normally, if the whole process is steady state, whatever that comes in should come out of this control volume, right? But in general, you know, in the non-steady state process, something that comes out will be different from that coming in. So Q plus partial Q partial x, the space coordinate x, times, let's say, I said this is a little piece of material, right? So infinitesimal material. So we use the thickness of material, dx. dx multiplied here. Okay? So whatever that comes in, whatever that comes out, they don't have to be same with each other. So what happens as a result? Well, as a result, the state inside this material will change, right? So it's simple bookkeeping process. Something comes in, something goes out, and that difference will contribute to the change of the state inside the material. And why is that difference? Well, it's a concentration of molecules, right? Normally we use N for the concentration of the molecules, of the impurities, boron and phosphorus, for example. So here, because of this difference, you know, the concentration change will be, well, concentration will be the function of not only the space coordinate system x, but also it's time varying. As I said, you know, it's not steady state problem anymore. So it will be partial n. Well, the concentration changes over time, so it will be partial t because of this input-output difference. Okay, and concentration is the number of particles, number of molecules per certain volume. So in order to count the total number of particle change, you need to multiply by infinitesimal volume. Okay, so if you write down the whole bookkeeping process, something coming in is positive, something going out is negative, and the change is positive if it is increasing. So you need to Q minus, set the equation like Q plus partial Q partial x dx. Well, of course, you need to multiply the whole thing by the area, right? Because flux is, by definition, number of molecules, number of particles that passes through the unit area per unit time, per unit area per unit time. So you need to multiply by the area to count the number of particles that are being supplied or that are leaving into or out of this control volume. So this difference will result in partial n, partial t, delta V. Delta V is the volume of the little element. Okay, now if you take this difference, you have minus partial q, partial x times dx times a equals to partial n, partial t, delta V. Alright? So this thing is actually, isn't that the volume? Area times the thickness, right? So this volume and this volume will cancel out, alright? So now you have this equation right here, right? And in this specific equation, what is the flux? We have already seen the flux can be defined as the number of molecules that are being driven by the concentration gradient, isn't it? Right? We call it a fixed law of diffusion. Actually, to be precise, fixed first law of diffusion. So Q is equal to, remember we use minus because the direction of diffusion is actually opposite to the gradient, and the constant of proportionality is called diffusion coefficient, and so this will be partial concentration gradient, right? Partial n, partial x. Why partial? Because n is a function of two variables, right? X and t, remember? Where did it go? Right here. Two variables. That's why we need to have a partial, right? Okay, so if you just plug in here Q into the equation above, what do you have? Minus minus becomes positive. So D partial, they are double partial, right? Square n and partial x squared equals to partial n, partial t. Indeed, does anybody know how we call this equation? It's a fixed second law of diffusion. Law of diffusion. Indeed, in our previous case of the oxidation, partial n, partial t was 0 because we just thought about steady state. But now, the whole process cannot be the steady state anymore, okay? So this little piece of equation is the equation that we need to solve. We ended up with this partial differential equation. How can you solve? Well, if you go back to your college student memories, you guys took the engineering mathematics 1 and 2. In engineering mathematics 1, you guys learn how to solve the ordinary differential equation normally, and other things of course, but the main theme was actually ordinary differential equation. And engineering mathematics 2, one of the main themes was actually partial differential equation, even though we learned something like complex variables and geometrical analysis and other things. But the learning the partial differential equation, the solving the partial differential equation was one of the main things. Most partial differential equations cannot be solved. That's why people use finite element methods, finite difference methods, many kind of the computational analysis method. However, in some cases you can actually solve partial differential equations. And that solution process is very important because you not only obtain a very nice formula, but also you understand the physics. That's very important. It's not just simple mathematical solution process that leads to the solution. It is the understanding of fundamental physics that actually matters in the whole solution process. That's why we try to look at some solution that are available for this partial differential equation. So for this specific partial differential equation, what kind of method did we use? For instance, we used to use separation of variables. We just think that function of many variables, for instance, 2 variables here, function of up to 4 variables, right? X, Y, Z, and T, right? In these cases, we just separate. We just assume that the function is multiple of single variable functions, you know, and then we separate them, and that leads to a very interesting problem, you know, and that problem is called eigenvalue problem indeed. Okay. Today I'm not going to go through such kind of process because it'll be used limited to certain kind of solution process. But for our case, we're gonna deal with the silicon. Let's say this is silicon with infinite dimension into the body, and that can be justified because, you know, this diffusion process occurs only at the surface, very close to the surface actually. Okay, it doesn't go all the way to the deep into the body of silicon. Okay, so we can assume such kind of zero infinite problem, and for that specific problem, there's a very nice solution process. Okay, so let me write down this equation one more time. Instead of this, I would like to write down partial square n partial x squared equals 1 over d partial n partial t. Remember, n is a function of 2 variables with the initial condition and boundary condition, right? What was the initial condition, right? Sorry, boundary condition. At the surface, whatever time it is, well, we'd like to assume a very simple thing. So you have a surface, and at the boundary, okay, we'd like to assume the simplest case. What is simplest? You know, concentration of the impurities at the surface just remains constant, right? Isn't that the simplest case, right? Rather than changing something, let's make it simple. Let's make the surface concentration constant. Constant at, for example, here, NS surface. How about that? All right. Well, that's the boundary condition, and the initial condition could be N. Wherever you go, well, if time goes to 0, is it 0? Yeah, 0. I would say 0 minus. No diffusion occurs yet, but you go some depth into the body, concentration will be 0, right? Initially there's nothing inside, and there's a pulse of the impurities at the surface. So it's really singularity problem. The singularity problem that 3 scientists solved to get the Nobel Physics Prize this year. Remember, Penrose, you know, he's the really good at, you know, modeling and solving these singularity problems. I'll talk about Penrose later on. Penrose, Roger Penrose, who's got the Nobel Prize yesterday, you know, on physics. I like him. So you got the equation, and you got the boundary condition, and you got the initial condition all together. And now we are ready to solve this with a special method. What is that special method? That special method is to use the insight into the structure of this equation, which teaches us the physics of this doping diffusion process. Physics of diffusion process. And that teaches us very important behavior of this doping profile. Okay, so what you really have is you will have a silicon. From here you have silicon and x-axis and surface profile. At the surface, concentration will remain the same. This is T0, for example. You just have a pulse of singularity, you know. And then just release it. As time goes by, driven by the temperature, you solve the diffusion, right? Because of diffusion gradient, you know, diffusion will occur, and it'll go like this. And diffusion will go more and more into the body of silicon as time goes by. So this is the T equals to 0 minus, remember, before diffusion occurs. And as time increases, T increase. Diffusion profile will become more and more flat and go deep into the silicon. And we assume that the depth of silicon is infinity, because compared to the surface, it's really a huge number. It's really the large number, you know. All right, then what happened next? You know, well, just take a look at this equation, and people try to come up with the function that can be defined not by two variables, but by a single variable, by mixing these two variables. How can we mix? Well, we can add them up, we can multiply them, we can divide one with the other, you know. And so it's really trial and error process, but during this trial and error process, we can learn the physics of it. So I try this, I try that, I try this number, I try that, I this combination. Well, what's really important is that you have square term here, and you have a singular term here with constant. And that gives us some kind of insight into this problem. So we can define a single variable as a mixture of two, which is x over, for example, square root dt. Okay? Why do I have this? Well, I try this, I try that, you know, eventually this works. How does this work? You'll see. And at the same time, just multiply by a number, 2 here, right here. Why 2? You see that. Actually, that makes our lives a lot simpler. Rather than having 1, rather than having 3, rather than having 4, you know, 2 is a much better choice. You know, you'll see that. Okay? So this definition that leads us to a single variable out of two variables, x and t, is kind of a mathematical choice of convenience, but at the same time, this teaches us about the length scale that is associated with the time scale. What was the dimension of d? Remember, it was like centimeter square per second. Please take a look at your previous note of oxidation. You know. So if you just put it there, take the square root, you see that the dimension of the square root dt is nothing but the dimension of the length, centimeter. So centimeter cancel out together, and it's nothing but a variable with no unit. Unitless variable. Isn't that interesting, really, right? It turns out that it's actually really the length of diffusion here is kind of comparable to dt, and we call this Einstein equation. Amazing, right? Einstein already noticed this physics. And this is a very important equation indeed, you know. The length of diffusion is proportional to the square root of time. So in a normal scale, macro scale, you know, this is like meters. Well, to achieve that, you need a lot of time indeed. Okay, for the molecule to diffuse, for example, inside the water, for the molecule to diffuse like centimeters or meters, it will take hours or days in the water, you know, for example. But even in the same water, if the size of such diffusion becomes like microscale or nanoscale, then it takes a fraction of a second for the molecule to diffuse. That's exactly what's happening inside the cell. So inside the cell, mixing is not really important, you know, because molecules will diffuse very quickly inside the cell. And the molecules can match with the other molecules many thousand times per second by diffusion. And that makes the molecular machine work. That makes the DNA that can be replicated and produce RNA, and RNA that can be translated into proteins. In your body, inside the cell, such kind of reaction occurs many thousand times a second by diffusion. So this is really an important insight about the multi-scale fabrication. Even though this fabrication I'm teaching is now about just the top-down approach, you can even learn some insight into bottom-up approach by diffusion machines, you know. Okay, so I'll talk about it much more, maybe somewhat detail later on if I can squeeze out more time for, you know, such lecture. But today, this is important. You know, we just define non-dimensional variable here, okay? And this approach is a very famous approach indeed. This is called, I forgot, what is this called? I forgot. I'll tell you later, sorry. What is it? Scale. What is it called? I forgot. Okay, let's focus on this problem. So during the explanation of the whole solution process, if something comes up to mind, I'll tell you. What is it called? Okay, let's keep this going on. Okay, so this is our definition, I said, all right? And the equation that's given is right here, you know, you see, right here with this initial and boundary conditions, you know, because in second order you need two conditions, you know. So first of all, by having this definition, now n of two variables now becomes n of a single variable. So in order to transform partial differential equation with two variables into ordinary differential equation with one variable, you need to go through chain rules, right? So some of the useful chain rules is actually, for example, here, partial partial t. So partial n partial t, for example, would be partial n partial, because we want to switch to a ordinary differential equation, dn d eta, and then since eta is a function of two variables, partial eta, partial t. So we can learn this partial, so it goes like this. All right. Okay, now what is partial eta partial t? Remember, eta is right here, so x over 2 square root d has nothing to do with t. Now partial square root 1 over square root t, partial t, t to the minus 1 over 2 power is 1 over square root t, right? So if you take the derivative, there will be obviously minus 1 over 2, and then if you subtract 1, it will be the result of this derivative. So minus 1 over 2 minus 1, minus 3 over 2. Minus 3 over 2 is t square, 1 over t square root t. So the result will be 1 over t square root t. This corresponds to t to the minus 3 over 2 power, okay? And then there will be minus 1 over 2. Is that good? Alright, so let's just leave it like this. And the next thing we want to try is actually regarding the partial with respect to x. So let's just take a look at this. Partial eta, partial x. What is it? X is simple variable, right here. So where is the eta? Eta was x over 2 square root t. So this will be 1 over 2 square root dt, isn't it? So the term we want to deal with here is this term, right? So partial square n, partial square n, partial x square will be partial x, partial n, partial x. Okay, what is partial and partial x? It will be dn d eta times partial eta partial x. Right? That's the chain rule we learned in the college calculus, right? The basic calculus, basically. Chain rule, Okay, now if you just plug in right there, it will be partial x dn d eta times partial eta partial x is 1 over 2 square root dt. All right. And since 1 over square root dt has nothing to do with x, you can just ignore it in applying this partial. When the partial is one more time applied here, it'll be d square and d eta square. And one more time, partial partial eta partial x, right? And 1 over 2 square root dt. Indeed, it turns out that partial eta partial x is the same thing together, 1 2, right? So it will be d square n d eta square times 1 over 4 dt. And this is indeed equal to the right hand side was 1 over d partial n partial t. Partial n partial t was right here, right here, right here. Partial n partial t. It's right here, right? So it'll be x over 4 square root d x over 4 square root d, isn't it? And 1 minus is there, 1 over t, 1 over square root t times t, right? And minus was there, remember? And of course dn d eta, dn d eta. I'm collecting the terms. So this term, same as this term, you know. Now is a fun time. Why is a fun time? Because we can eliminate numbers, you know. Sorry. Forget it. Yeah, numbers. Eliminate the numbers. 4, d, t, t. What's remaining on the right hand side? So left hand side, everything's gone. What's remaining on the right hand side is x over square root dt. So minus x over square root dt times dn d eta. Remember, this is the variable that we use. Now it comes up to my mind. Okay, so this definition, we call it similarity. I'm happy that this idea comes up to mind. Variable. Similarity. These two variables are similar. You know, this length scale and this diffusion scale, they are similar. They are similar to each other. You know, leading up to the Einstein equation. All right. So we call this similarity variable. The eta was similarity variable like that. So what is x over square root dt? That is twice the eta. Okay. That's how we introduce 2 here. Why is 2 important? You'll see soon. So this will be nothing but minus twice the eta dn d eta. Look, finally we have arrived at the what was this, by the way? That was this part, right? Arrived at ordinary differential equation, our partial differential equation. So if I rewrite this, dn square d eta square equals to minus 2 eta dn d eta. Remember, we started from partial differential equation. We introduced the similarity variable, and then now we are ended up with the beautiful ordinary differential equation. Okay? During that process, what we have learned is that indeed, because this is a diffusion process, diffusion is actually proportional to the square root of time. You know, it's not directly proportional, it's a square root of time. Okay? So that's very important. So can we solve this equation? We'll try next time. Thank you. Have a good weekend.